Welcome back, everyone. In this video, we will be continuing the section on log derivatives and logarithmic differentiation. So in the previous section, we did a little bit more with the derivative of the natural log using the chain rule, kind of notice a pattern to help ourselves do the derivative more quickly. And also, in the last problem, we looked at the graph of a log function and its domain, and we compared it to its derivative. And we saw that you have to be kind of careful about using the derivative. Well, really the point of that is to say anytime you do a derivative with the natural log or any log, but we pretty much stick to natural log, is that you can add in numbers as far as your formula goes that's not in your original domain, and you can't really plug them in. So when we do anything with logarithmic differentiation or a log derivative, keep in mind that our formula works where our original formula works. That's the main thing about derivatives. That's really all we care about. But you could, in theory, be asked a hypothetical question, explain why so-and-so, the derivative formula does not actually valid for specific x values. But I won't be doing that. I'm not interested in tricking you. I just want to let you know that that's possible. All right, so logarithmic differentiation, what is it used for? Well, it's kind of used for one specific reason, and that specific reason is to make your life easier doing derivatives, but it's actually a technique that can be used in two different ways. It can be used to actually compute derivatives of functions that without logarithmic differentiation you cannot do. It can also be used to compute derivatives of functions that we can already, but make it a lot easier. And we kind of saw in the first example in the first video that, there are functions that we don't have to use logarithmic differentiation for. There are functions that we don't have to use log rules at all for and still do the derivative. But the first example we did, it was a lot easier if we did log rules. The ones in this section and logarithmic differentiation are going to be similar in nature. You're just not going to start with a log in the equation. So a couple classic examples that you use logarithmic differentiation for are classes of functions like this, x to the x, where you can't actually do it without log differentiation. And to the point here, we can't actually do this yet. The reason why we can't do the derivative of this yet is our power rule only works when the exponent is just a number. Our variable is x, and we have x to the x power. We have a variable in both spots. But at the same point, our rules for the exponential derivatives, when x is in the exponent, we need the base to be just a number. When they're both x, when they're both a variable, we cannot do them yet. So what I'm writing here is it cannot be done without log differentiation. I'll abbreviate it log diff so I don't have to keep writing the entire thing out. Now, the one on the right over here was the second kind of example I was talking about. We can do the derivative of this because the square root is something raised to the 1/2 power, and we've actually done something like this before with the chain rule. So we can do this with the chain rule, but log differentiation will actually make it a lot easier. And we'll see examples of both types below. Focus mainly on this one because a log differentiation is an actual requirement to do this one, but I just want to show you an example of how log differentiation will help. Now, the general idea behind logarithmic differentiation, it's a general technique, like I said. There's not necessarily a formula at all for it. It says do the natural log of each side, use log rules to simplify. This is going to be a requirement. If you don't use log rules to simplify, you're kind of defeating the entire purpose of doing log differentiation. And then implement implicit differentiation. Now, it sounds like we're going to be doing a lot. Well, we are going to be doing a lot, but it's a lot of little different things. It's not going to be a lot of big things. All right, so with that said, before we get to the problems, I want to talk about the 3 log rules that we can use. I mentioned two of them before in the first example we did in the previous section, but I wanted to go ahead and take this time to solidify those rules. So if you're not familiar with them, I like to write them down, but also write them in words. And the way I've written them is how we're going to use them typically. We're pretty much going to be reading these equations from left to right, even though you can read them right to left. So the first one here says, if you have a log and the inside is raised to a power, it has to be the entire inside raised to the same power, then you can bring the power out front. That helps a lot, and we saw it in the first example because it'll help get rid of a chain rule. So this one will help get rid of a chain rule. Now the multiplication, if you're multiplying inside a log, that becomes addition outside, and this will help get rid of product rules because we'll go from something that's being multiplied to something that's being added. And then lastly, divisions. Divisions require the quotient rule, but if you're dividing inside a log, you can make it subtraction outside. And in this case, it's getting rid of the quotient rule. We would just do the derivative of each part. But once again, the general idea is do the natural log of each side, use log rules to simplify, then do implicit differentiation. All right, and once we get started on one, it'll hopefully make a lot of sense and it won't be nearly as terrible as it sounds. All right, so the first one you have here is we want to use logarithmic differentiation to find y prime if y equals x to the 2 cosine of x power. Now the reason why for this one we absolutely need logarithmic differentiation is we have x in the power and in the base. If you have both, then you have to use logarithmic differentiation. There is not another way we know how to do it. Okay, so what's the method of logarithmic differentiation? The first step is do the natural log of each side. And by each side, we mean each side of the entire equation. So you're going to do the natural log of y equals the natural log of x to the 2 cosine x power. Now, this is the main reason why we have to use logarithmic differentiation here and do the natural log of each side, is this gets rid of our issue. We have the log rule that says if we take the exponent that's being raised inside the power here, well, we can move it out front. And that gets rid of our problem because we'll no longer have an exponent and a base both having x. In fact, we're not going to have an exponent at all. So this is using rule number 1 here. We're bringing the power out front because it's the entire portion of x. So the entire inside being raised to that power, which is just x. Okay, so this simplifies. We get 2 cosine of x times the natural log of x. Now keep in mind, we've only done algebra here. We have not done any derivative rules. And what I want to go ahead and do is rewrite the equation we currently have. We have the natural log of y equals 2 cosine of x times the natural log of x. Now this doesn't seem that great right now, but remember the steps we outlined. I'll go ahead and go back up here. We do the natural log of each side, use log rules to simplify. We've done that. And now we want to implement implicit differentiation. Why? Well, because we want y prime, and we know to get y prime, we have to do the derivative, and a y prime will pop out of here. And, we don't want to really try to go back, because if we try to go back to y before we do y prime, then we're just going to end up right back with our original equation. So at this step, I would consider this right side simplified because there's no exponents, there's no multiplications in logs, there's no divisions in logs. We only have x inside the log, so there's nothing else to try to do. So now at this step, I would do the derivative of each side. That's what implicit differentiation says to do. So do implicit differentiation. And when we do that, we're doing it with respect to x. We know that from the implicit differentiation section, y prime means y is our main variable and x is the independent one. It's the one we're doing the derivative with respect to. So we got to do d of dx on each side. And whoops, started looking at the left side to start writing down the right side. So we got to do the derivative of each side. It looks like that. This should be a little bit easier than a lot of the implicit derivatives we did in the last section, because there's only x's on this side, which means we're not going to have to worry about really the chain rule, at least with weird things of y. We only have to worry about the chain rule over here. The derivative of the natural log of y, well, like I mentioned in the last lecture, is that you can sort of shorthand it, and it's a lot better right now if you use that shorthand, because the derivative of the natural log of y from the chain rule, since y does not match x, it's the derivative of the inside on the top, which is y prime, over the inside itself, which is y. And this is, for a lot of people, when they talk about, if they use formulas referencing logarithmic differentiation, they'll write this y prime over y over here, because you'll do the same steps. But the main thing is, if you try to memorize a formula, which is fine, you're still going to have to go through the process of simplifying the right side anyway. So I don't think it's worth trying to memorize a formula. It's better just to memorize or understand the technique. All right, now on the right side, we can just do the derivative using the regular product rule. Luckily, we have only x's inside our function, so we can just use the normal product rule. The derivative of the derivative of 2 cosine of x would be negative 2 sine of x times the second, so times the natural log of x, plus the first, which is 2 cosine of x, times the derivative of the natural log of x, which is just 1 over x, because we have just x inside. Right. Now I want to go ahead and simplify. I'm going to try to just simplify the right side here, but you'll notice that there's really not going to be much to simplify. Now, we talked about this before. The reason why there's not really anything to simplify is because we have an x with a cosine here. We have a sine with a natural log here. There's really nothing in common. If you wanted, you could take the 2 out, but there's not going to be much else to do. So we get y prime over y equals, if you want to take the 2 out, go ahead. We have negative sine of x times the natural log of x plus cosine of x over x. And now it doesn't really look like we're even close to done, because we want to get y prime by itself, and we still have this y. Well, the thing is, we can multiply each side by y now to get y prime by itself. I'll go ahead and multiply it in the front just so I can leave it out front. And we get y prime equals y times 2 times all of this. Well, the thing is, we have a formula for what y is. It's x to the 2 cosine of x. Why is that helpful? Well, now we can go ahead and just plug in what y is, because we do want a formula with just x in here. We started with y equals, so we know our derivative formula should have just x. And if you plug in what y is, we got x to the 2 cosine of x, then that's what y is. And then we can just write out the rest, 2 times negative sine of x times the natural log of x plus cosine of x over x. Close that parentheses, and then we're done. There's very little you can try to do to simplify here. There is one thing, but I think it's not even bothered. There's no really reason to simplify it. The reason is, if you try to simplify it, kind of this x that's in the denominator here almost gets hidden, and then it might throw off some sort of division by 0 that you don't necessarily see. So in my opinion, it's just best to leave it like this. Right, now we do have an extremely messy formula, but this is the method of logarithmic differentiation. Do the log of each side. The first step when you're simplifying is always going to bring exponents out front. But because we didn't have any multiplications or division inside the log after we did that, we were simplified. Then once we got the right side simplified, we did the derivative of each side. You're always going to have the natural log of y on this side, which means when you do the derivative with implicit differentiation, you should always get y prime over y here. The only thing that will change is, because you can have different function over here, you'll get a different derivative. But the method is always going to be the same, because then at the next step, you have y prime over y, and you have to get the y prime by itself. You're always going to have whatever y is over here as well. But I can't stress enough, you do not want to try to memorize some formula for logarithmic differentiation. I don't think it's worth it by any means. The method is what's most important. All right, so with that, I think, really because it's a method. If you want to go ahead and pause and try to do the derivative of this, go ahead. One thing is if you want to try to do this by yourself before I do it, remember that the square root of x equals x to the 1/2. So you can actually simplify this before you start to do even the natural log of each side. And I'm actually going to go ahead and do that first. So I'm just going to simplify this because we know when we do derivatives, we don't like square roots. So let me go ahead and when I plug this in, we get f of x equals square root of x is x to the 1/2. That's to the 3x power. And our derivative rules say multiply the exponents here. Well, 1/2 times 3x would be 3x over 2. And I would do the derivative of this. This is going to be much simpler than doing the derivative of this just because you don't have to worry about the radical anymore. It's already taken care of. All right, so what is the method here? Well, one thing I would probably go ahead and do is just switch f of x to y to make it a little easier to read. So we have y equals the function x to the 3x over 2 power. Right. And the first thing to do with logarithmic differentiation is always do the natural log of each side. You can't do log rules until you have a log anyway. Since there's no log there, you got to do the natural log of each side. So we get the natural log of y equals the natural log of x to the 3x over 2 power. And here, it's pretty much the same setup, even though the previous one had a trig function in it and this one's just exponent with x in it. The idea is always going to be the same when you have something like this. Bring the exponent out front. We get the natural log of y equals 3x over 2 times the natural log of x. Right? Is this right side simplified? Can we do the implicit derivative now? We can because the inside is just x. There's no multiplications, no divisions, no powers. We're good to go. And now we do implicit differentiation. We do the derivative of each side with respect to x. Now we might already be comfortable with what's going to happen here based on the last one, but let's just go ahead and very clearly write down what we're doing before we skip any steps. So we do the derivative of each side, the implicit derivative. And then what's going to happen? Well, we know on the left side, it's going to be the same thing as last time. The derivative of the natural log is the derivative of the inside. Since it's not just x, we have y prime over y. And now to do the derivative of this, we have to use the product rule again because we have 3x times, or 3x over 2 times ln of x. The derivative of 3x over 2 is 3 over 2, the first, times the second, times the natural log of x, plus the first, which is 3x over 2, times the derivative of the second. The derivative of ln of x is again 1 over x. Since it's just x, nothing to do on the top. And if you can simplify this, which we actually can simplify this a little bit, go ahead and do that. You can take the x out exactly here, which is kind of nice. And what are we left with? We're left with y prime over y. Notice that the back fraction here is just 3 over 2 because it's only 3 over 2 times 1. And we have a 3 over 2 in the front as well. So we can take the 3 over 2 out. We have the natural log of x in the first one plus just 1 in the second one because 3 over 2 is all we had back here and we took it out. And then just like last time, multiply each side by y and you'll get y prime by itself. And if wherever you want to multiply by y, the front, the middle, the back, it doesn't matter. You know, just do it somewhere you're allowed. Can't do it inside here, of course. All right, so we get y prime equals 3 over 2 times the natural log of x plus 1. And then we multiply by y. And I would highly recommend multiplying by just the simplified one, not the original one, but the simplified one. So we get x to the 3x over 2 power. And technically we were asked for f prime of x. So if you want, just take this last step, switch y prime to f prime of x. And then you'll officially be done. But that's all we've got to do. And even though I think at the onset, maybe as I described it before, what we're going to be using this logarithmic differentiation for, you were a little more concerned with doing the derivative of this than something we could already do. But this is honestly about as messy as it can get. If you don't realize to use the exponent rules to simplify first, then this is a lot messier because you're going to end up having the square root of x inside here. But always think about switching radicals to the exponents, and hopefully you can see how to simplify it before you do anything else. All right, so the last one I have here is just an example of a logarithmic differentiation on something that we can already do the derivative of. So we know how to do dz over dt of this. We could just rewrite the radical, which we're going to do anyway. So I'm going to go ahead and do that, just like we've done for all of them. Anytime we have a radical, we rewrite it. And the square root is just the 1/2 power. Now there's nothing really to do here. With the previous one, we had another exponent so we could simplify. There's nothing really to simplify anymore here before we do the log rules. Right? But we know how to do the derivative of this. We could use the chain rule, then multiply by, that would be the power rule first, then we rewrite the inside, subtract 1 from the power, and then multiply by the derivative of the inside. And to do that, we would have to do the quotient rule. Well, let's just see how great logarithmic differentiation is. Do the same steps, even though we could already do it the other way. So we do the natural log of each side. We get the natural log of z equals the natural log of this big fraction. We have t minus 5 over t to the 6th plus 1 to the 1/2 power. And we want to simplify. Pretty much anytime you do the log derivatives, you're looking for 3 things to try to simplify. You want to bring exponents out, you want to break up multiplications, and you want to break up divisions. Now, one thing I want to make sure on here is which one you want to do first. This one, we're going to have the exponent that we can bring out first. Why? Well, because it's all raised to the same power. Now, if you had a fraction, but the numerator was raised to a different power from the denominator, you would break up the division first. But this is all raised to the same power, so we can bring the 1/2 out front. And we get 1/2 times the natural log, and then the inside is now just our fraction, t minus 5 over t to the 6th plus 1. But we don't want to stop there. Right? We have a fraction here. We can break up a log over a fraction. If we tried to do the derivative at this point, we know we would still have to use the quotient rule, but our other log rule says, so we're going to have a 1/2 out front. Because it's going to become subtraction, I'm going to put a big bracket around what's going to go inside. And our log rule says division inside is subtraction outside. So this entire ln of t minus 5 over t to the 6 plus 1 is the same thing as the natural log of t minus 5 minus the natural log of t to the 6th plus 1. Now, kind of think about what's going to happen here is now we're simplified. We can't break up logs over addition or subtraction inside, which means these are stuck like this. And the 6th power here, it's not raised to the whole thing, which means this is completely simplified. At this point, this is what we would do the derivative of each side of. Let's go ahead and do that. I'm going to actually rewrite what we have first, the equation, but I'll leave room to write in the derivative. So we have the natural log of z equals this in orange, 1/2 times the natural log of t minus 5 minus the natural log t to the 6th plus 1. And now I want to do the derivative of each side. Well, our derivative we're doing the letter with respect to is t. So d over dt. We want to do the derivative of each side. And now if it helps, you can go ahead and take this 1/2 and bring it out front using our derivative rules. So I'm going to go ahead and just visually do that. That's a derivative rule. Of course, that has nothing to do with the log rules. We're done with log rules now. I'm going to bring the 1/2 out front just to make it a little bit easier to do the derivative of this side. A little bit easier to see. All right, now on the left side here, what is the derivative with respect to t of the natural log of z? Well, the natural log, because the inside is not t, it's z, we do the derivative of the inside, which we can write as z prime, over the inside z itself. Now, what about the right side? Well, I have this 1/2 out front, so it's just going to hang on, be a part of the party. I'll put my big bracket again, and then we want to do the derivative of each one of these. Well, because it's linked by an addition or subtraction, we know we can just do the derivative of each part. And the derivative of a natural log, we have the derivative of the inside. The derivative of t minus 5 is 1 over the inside, t minus 5. So that's the derivative of this first part. We have a minus, so I'm going to bring down the minus. Going to have another fraction, and the derivative of the inside of this one is 6t to the 5th over, and then this is over just the inside, t to the 6th plus 1. Now, as messy as this looks, and we're not actually going to be able to simplify it very much at all. You pretty much just do the one step we've been doing above. To get z prime, which is dz over dt by itself, we're now going to multiply each side by z. And I'll just do it on the back here since that's where I have room to write it. And when we do that, if you want to leave z prime as z prime, that's fine. Just understand it's the same thing as dz over dt. So I'm going to switch it just to match what we were asked to write. We've got 1/2. Now the c is multiplied in the back, but I'm just going to actually move it up here because the order of multiplication doesn't matter. Z is the same thing as t minus 5 over t to the 6th plus 1 to the 1/2 power. And then in my brackets here, I'm just going to rewrite what's here because this isn't going to help if I try to simplify. So 1 over t minus 5 minus 6t to the 5th over t to the 6th plus 1. The only thing I could actually really do to try to simplify this is go ahead and try to get a common denominator in here. But because these powers are so different, when you do it, even if something cancels out, it's not going to really help. So I would recommend just leaving it like this. And a lot of times when you do logarithmic differentiation for something that can already be done another way, it looks pretty messy. One thing I always like to specify is that if we had done the derivative of this from scratch and we did the chain rule, so we bring the 1/2 down, we rewrite the inside, subtract 1 from the power to the negative 1/2, then this would be a negative 1/2. That's sort of the setup we would have. And then this thing multiplying inside would be the derivative of this using the quotient rule. And we know from past experience that simplifying with the quotient rule can be really, really annoying and troublesome. But this is correct. If you had done it the other way, if formula-wise, your answer might look a lot different, but it would be the same thing as long as you do it correctly. All right, but that is the idea of logarithmic differentiation. Use it if you'd like on these sorts of problems. I recommend practicing it, but just know that it's absolutely required on both of these problems. You can't get away from doing logarithmic differentiation if you have x in the base and in the exponent like this. But that is it for this section. I know both the videos were kind of long, but I think they got broken up pretty well. And I will see you in the next section.